The topic is related rates. Corresponds to section 3.10 if you're following along in the Thomas Calculus textbook. Um, so before we get, this is really an application topic. A lot of this involves reading word problems and translating them into the correct calculus to solve the problem. Before we go on, I know this topic has a reputation as being a bit difficult. There's a fairly well-known manual it's a printed manual from the 1980s where the author sort of in a whimsical style created some sort of dangerous bend symbol like a road sign. So in areas that he thought were particularly complicated, he'd print this graphic of a dangerous bend symbol. So you'll notice that up here I've put not one but two dangerous bend symbols on this topic. The fact is, I think that this topic has a little bit too much of a reputation of being difficult, but I do want to just advise you to pay attention to it carefully. It can be a little bit tricky, but honestly, there are really only a small number of types of problems that occur, and they're all fairly similar to each other. So anyway, with that, let's begin. In order to even talk about the topic, there are a couple of principles that we need to get clear on. First of all, I think I've mentioned this before, but the d operator that we use in calculus, as in dy over dx, means change in or change of. So if I talk about dy, what I mean is the change of y. And if I talk about dx, I mean the change of x. If I put one over the other, I'm talking about the ratio of how much one changes relative to how much the other one changes. As I've written here, I said dy over dx really means like the ratio of how much y changes for every unit x changes. Um, Although we refer to this expression dy over dx as the derivative of y with respect to x, each of the individual terms, the dy and the dx, has its own name, and that name is differential. Each of them is called a differential. We'll get to the importance of that really in the next section. But these are independent objects. The reason that we care about defining what those are is for point number two, which is that normal algebraic operations work on differentials. Um, Strictly speaking, a differential is in what's called an infinitesimal quantity. It's so small that it can't be measured. And if I'm being purely strict about it, I have to say that algebra does not apply to these quantities. But in reality, and in the way that we're using these quantities in these problems, the normal algebraic operations do actually work, which is one of the reasons why dy over dx is such a good notation. I've just put up an example here that if I know what dx over dy is, let's say, I know that many of you say, wait, isn't it dy over dx? Well, it depends on what you mean. There's also such a thing as dx over dy. If I have dx over dy times dy over dt, I can simply do this cancellation and get dx over dt, and that's a completely valid thing to do. That's useful if, let's say, you want to know how much x changes for every unit that t changes, but instead all you know is how much x changes for each unit of y and how much y changes for each unit of t. You can figure out what dx over dt is from that. The other thing, as I mentioned, you're saying, wait a minute, isn't it dy over dx? If I put 1 over dy over dx, in other words, the reciprocal of dy over dx, I get dx over dy. Completely valid operation that you can perform with differentials. Um, so the third principle is this, is that every variable can really be thought of as a function of time. We sort of imagine that if I have, let's say, the parabola y equals x squared, let's say on the interval, the interval from x, x equals 0 to infinity, we sort of imagine that x is the independent variable and y is a function of that. But what we could do instead is imagine that we have some object, maybe a particle, like we called it in the last um, in the last section, one of the more recent sections. We can imagine a particle moving along this path, in which case we can sort of picture that the position of the particle, both its horizontal and vertical positions, are really functions of time. That, give me a particular time, t equals 1, t equals 2, I'll tell you how far to the right that particle is and also how far up it is. So it really does make sense to think of all variables as being functions of time. So really there is no x and there's no y, there's just x of t and there's y of t. And we're going to be using that principle. So anytime you see an x or a y or a v for volume or an a for area, you have to think of them as though each of these is really x of t, y of t, v of t, a of t. They're all just functions of time. And that's useful because it means we can find their derivatives with respect to some imaginary variable t. So let's just do some examples with those operations. Um, let's suppose, for example, that dy over dt is equal to 5 and dx over dt is equal to 3. Let's find dy over dt. Well, based on what I had shown earlier, what we know is that if I take dy over, uh, sorry, let's find dy over dx. That's the question. So what I'd shown earlier is that if I take dy over dt times dt over dx, by cancellation, um, that should give us dy over dx, which is what we're seeking here. So we have dy over dt. In other words, this is 5. We don't have dt over dx, but we do have dx over dt. So we can find dx over dt simply by observing that we can find dt over dx simply by observing that dt over dx is equal to 1 over dx over dt. We'll just take the reciprocal. Well, since dx over dt is 3, that means that that's going to be 1/3. So dt over dx is equal to 1/3. And that means that we can conclude that dy over dx is equal to 5 times 1/3, which is 5/3. So what I have here really are two constant rates of change. I'm saying that the rate at which y changes 5 units for every unit that t changes, and x changes 3 units for every unit that t changes. So I can determine that y changes 5/3 of a unit for every unit that x changes. That's just what the algebra shows. Um, let's just do one more of these, a little bit more complicated. Let's suppose that y equals the square root of x and dy over dt is equal to -5. So let's find dx over dt when x equals 36. Well, what we have here is we want to find dx over dt, and we have dy over dt. I could certainly find dx over dt if I had dx over dy and then dy over dt. So this is given, and it equals -5. This I don't have. I don't have dx over dy, but if I did, we can see that I'd certainly be able to find dx over dt just by this multiplication. What I can do, however, is since I have y equals the square root of x, I can say that dy over dx is equal to the derivative of the square root of x, which we've done many times before, is just 1 over 2 root x. Okay, so that's dy over dx. That means that dx over dt, oh sorry, I need to actually invert this. I need dx over dy, but that's fairly easy to do because that means that dx over dy is just equal to 1 over dy over dx, which is 1 over 1 over 2 root x, which is 2 root x. So dx over dt is equal to 2 root x times -5. And just to be clear where this comes from, this is dx over dy, and this is dy over dt. The only thing is that dx over dy, as most derivatives do, includes x. In other words, I don't know what number it is until I know what the value of x is. But fortunately, this is given to us in the question. We're told what x is. So at x equals 36, dx over dt is going to equal 2 times the square root of 36 times -5. Square root of 36 is 6, so that's 12 times -5, and the answer is -60. These are fairly abstract versions of the problems that we're going to be doing. I'm just giving you equations, giving you some derivatives, some equations from which you can find derivatives. There are a few problems at the beginning of the section that ask you to do exactly this, but the main point of this section is to be able to take a word problem, translate it into these kinds of facts, and then solve the problem.